Hello, hello, and welcome. Thank you for showing up. So next I want to introduce Aaron Foster. Aaron is a senior network engineer at Corsica Technologies. He provides architecture and consulting services to clients in several business sectors. Aaron holds several notable certifications, including the OSCP and CCIE, which is just absolutely incredible. So congratulations there. Aaron will be discussing encrypted traffic and the modern firewall. Everyone, please welcome Aaron.
Check 1, 2, check 1, 2. All right, thanks for having me. Like I said, I'm Aaron, Fort Wayne native. It's really exciting to see this conference come to Fort Wayne and just the Fort Wayne tech scene really kind of coming alive, especially with the advent of remote work. We can really work for companies all over the country, so who knows who lives in Fort Wayne and can be a part. I'm a network engineer at Corsica. This talk is opinions on my own. Just want to throw that out there. Corsica is a sponsor. I'm presenting as Aaron today. I do like building with Lego. It is Lego, not Legos, just to throw that out there. And woodworking and Macs are better than PCs. So you can fight me later. All right, let's see if this will work. And it's not, oh, there we go. Okay, so one of the things I do is I work from home. A lot of times I will have technologies and things like that. I'm building. One day I had a big stack of firewalls in my office. My daughter said, what is that? What is that? I was like, well, it's a firewall. So we kind of talked through firewalls and things like that. And this was maybe 6 months ago. So I asked her when I was doing this presentation, hey, Maddie, what's a firewall? She told me, well, firewalls keep the internet bad guys out of your work office. And that's really the goal here. We want to keep things that are out, shouldn't be, come in. We want to keep them out and let the things that should come in go ahead and come in. So to talk through the modern firewall, let's kind of talk through how did we get here? Where did the firewall start? So earliest reference I could see to a firewall, and I may just have to go to point, there we go. 1988, Digital Equipment Corporation started with the packet filter. As the internet began to grow, they realized, hey, we need to go ahead and limit things that go out and things that come in. This firewall was very basic. It's what we call stateless. We would have to specifically define traffic comes into our server, but then we had to also then allow that traffic back out. 1989, AT&T Bell Labs came with the connection-oriented firewall. We know that if we allow traffic in, hey, we just need to automatically allow that traffic out. That began to build a connection table or connection tracking. All right, I'm just going to go ahead to... So in 1991, the problem became aware that with these connection-oriented firewalls, we could fill up that connection table with malformed traffic. We could go ahead and send bad HTTP DNS requests, and we could fill that connection table up. So in 1991, firewalls became application aware. Hey, we're going to look at the packets. We're going to see that's a bad HTTP request. We're just going to drop that. We're not going to let that fill our connection table up. In 1994, Check Point releases Firewall 1. This is really the first commercially available firewall. It starts to where you can go and buy a firewall off the shelf for your organization. 1998, the Snort project starts. Snort is an open source IPS engine. This really starts to add additional intelligence and functions to the firewall. 2004 is the advent of UTM, Unified Threat Management. Let's take all of these different boxes. Say we had a box doing IPS, we had a box doing application control, those sorts of things. Let's combine that into one device, one rack unit. 2008, Palo Alto takes it a step further and starts calling it the next generation firewall. Similar to the UTM appliance, however, more unified in that the different modules kind of know what they're doing. Some of it's marketing, some of it's just a more cohesive package for that. One thing not on here, 2012 is when I deployed my first firewall. It took me forever, and it was a good learning experience, but definitely kind of looking back now, I was like, man, I could do things differently there. I have been lucky, actually, with that specific customer now to refresh firewalls for them 3 times. So to kind of learn to grow with that, so that was a great thing. All right, so let's talk about the next generation firewall. What are the components of a next generation firewall? What are the big things, and how do we get there? Big things we've got is intrusion prevention, gateway antivirus, application visibility, web filtering, and threat feeds. So what are those different things? Intrusion prevention is a system of rules and analysis. It's going to look at your packet headers. It's going to look for maybe specific patterns that match known attack signatures. It's going to look at the content, the actual messages. Say you've got a SQL injection you're trying to prevent. It's actually going to look at that packet body, see those SQL injection, and then drop that. Anomaly detection as well. So anomaly detection is it baselines your network traffic. It's going to know here's our normal baseline for our networks, and we've now deviated from that. Is that something that needs to be addressed? Gateway antivirus. Similar in ways to endpoint antivirus, it's going to be hashing files as Cs go through the firewall, looking for known malicious files. There's often cloud sandboxing. We don't know the condition of that file. Let's go ahead and send it up to the cloud, execute it, and see if it's malicious or not. And then retrospective alerting as well. Because we're aware of the files going through our firewall, we can keep a list, keep logs of that. If later a firewall or later a file is deemed malicious, we know now, and we have records and logs of where that file went within our network. Application visibility. So this is looking at your traffic and looking to classify it. This works for non-web traffic. It's really across the board. So this is your FTP, skinny, SIP, those sorts of things. And this is really good for traffic management, for building QoS policies and those sorts of things. Classifying your traffic and being able to write rules around that traffic. Web filtering, let's keep the kids from looking at porn. We've got the categories that it's based on. We've got, this generally is for web traffic, HTTP, HTTPS. We'll talk about some challenges with HTTPS and content filtering later. And then content matching. Actually, a customer one time gave a whole long list of these bad keywords that they wanted to keep the kids from looking at. So you can just throw a bad list of words at it, and it's actually going to look at the web traffic and determine which, and just look for those words and covers you if your categories don't actually match. And then threat feeds. So threat feeds are lists of maybe fully qualified domains, IPs, file hashes, those sorts of things that are updated either by vendor or open source and downloaded to your device. This is great things like botnets, known bad IPs, those sorts of things that your firewall is aware of. And rather than you having to go and maintain a list of bad IPs, things like that you want to block, it's automatically updated. One thing I have found is you do get what you pay for these. With a company, say a Cisco Talos, Palo Alto Wildfire, Unit 42, those sorts of things, generally they are updated. They're updated right away. They are pruned if there are IPs that are no longer malicious. Their open source feeds have a lot of the same features, but they may not be pruned as quickly as you may have IPs that have been reused, rehabbed, that sort of thing, but they're still on those open source lists. All right, so we've talked about the firewall. Let's talk about web traffic encryption. Talk about how we got here with traffic encryption, and then we'll get into potentially impacts. So in 1995, there was a company called Netscape. I'm just old enough to remember a little bit of the Netscape Navigator browser, but in 1995, Netscape, they realized that we needed a way to protect traffic on the internet. We needed a way to secure traffic from point A to point B to, one, ensure it stays private, but then two, to ensure that that traffic has not been modified in transit. They released SSL 1.0, kind of at a conference like this. Within 10 minutes of releasing it, someone had already proven it to be ineffective. And so they went back and released SSL 2.0, which is really kind of the foundation of a lot of the encryption that we have today. In 1999, the IETF took over that standard and rebranded it as TLS. Still very similar to SSL. And over the years, we've had some changes, cipher suite increases, those sorts of things, but protocols largely stayed similar in how it works. Well, in 2018, TLS 1.3 was released. I almost think this should be TLS 1.2 in a way. It's a major change kind of in how TLS works and the impact to your organization and to the firewall. All right. So the foundation of SSL and TLS, which interchangeably terms, is a function called public key cryptography. So it's basically a concept of we have a certificate authority. This is a point of trust. It can then go and sign certificates and give you a certificate that you can use on your web server. That web server can then present that server to clients as they connect, and then the clients have the option to trust that certificate or not. One of the great things about these certificate authorities is operating systems ship with those certificate authorities already trusted. So your VeriSigns, GoDaddy, Sectigo, those sorts of things already come trusted. It's a very high security, very high trust environment, in that if there's a compromise at these root certificate authorities, anyone can then grab a cert, and I can masquerade as Google. So there's a lot of trust in the industry placed on these certificate authorities. That is how we're able to have the internet at large, is that I can go to that certificate authority, grab a certificate, and then any client or user that connects to my server will go ahead and trust that. Let's kind of look at public key cryptography and talk through how it works. I was concerned about the text on my slides being too small, but I didn't realize the screen would be 50 feet tall here, so there was no trouble there. So say you have the concept of, I have some data that I need to transfer, and I don't want anyone in the middle to be able to see that data. So in instance, I've got BSidesFortWayne. I'm going to go ahead and run that through the public key of my certificate. It is going to encrypt that data. We call that the ciphertext data. And then I'm going to send that to my web server. The web server has the private key, which is the other half of the certificate, and it can decrypt it. So I get BSidesFortWayne on the way out. So how is this used in SSL or TLS and the handshake? Well, when I go to connect to a web server, my client sends a hello to the web server. Web server sends a hello back and then responds with its public key. That's checked against my operating system and confirmed that, yes, I do trust the certificate authority that signed that public key. My client then uses that public key to go ahead and build a session key. For up until this point, the handshake has been asymmetric. I've got a public key from the server. I can encrypt my data, send it to the server. My client doesn't have a public key from a certificate authority. There's nothing there for the server to trust. So we've got to get from a asymmetric to a symmetric. And we do that by the public key going and encrypting that handshake. And then my client can send the session key to the server. The server can decrypt that session key with its private key and then go ahead and respond using those session keys that have been established. So up until at this point, we've been talking SSL version 3 through TLS 1.2. With TLS 1.3, there's a big change to that handshake. We've gone from kind of the 4 steps I had earlier down to 2. This is great for mobile devices, shortens the handshake required. It also increases security. So the client, in this case, sends a hello and initiates what's called a Diffie-Hellman exchange. I don't understand the math. There's logarithms involved and things like that, but it's basically server and client can both do a math problem on either side and come up with the same value. But anyone that sees the data transferred can't use that math problem to see that data. So we've got our Diffie-Hellman exchange. Client and server go ahead and come up and build that two-way traffic. The big difference with TLS 1.3 is when that server sends its public key to the client or certificate, that is already encrypted. That session key has already been built. So from the firewall perspective, we don't see that certificate pass to the client. So that's going to cause some issues for us in a lot of these next-gen firewall features. So let's talk adoption here. Google 2022 estimated that 95% of web traffic is encrypted. 63% of that being TLS 1.3. And that was as of 2021. So at this point, vast majority of our traffic is encrypted. Vast majority is potentially using TLS 1.3. Great for security, great for privacy, maybe isn't the best thing for our firewalls. But you know who else has adopted TLS is malware. According to WatchGuard, 70% of malware command and control traffic is encrypted. Obviously, that's an issue. If the traffic is encrypted, we can't see it. We can't run our firewall features on that traffic, and we run into issues. So let's talk through kind of some of the problems here. So I'm a big fan of Wireshark. It's a great tool for network engineers. Highly recommend if you don't know Wireshark, it's great resources out there. Go and look at Wireshark. So let's kind of look and see at a packet, at a handshake that happens for a TLS 1.2 client. So here in the Wireshark, you can see in our TCP header here, we've got our source and destination IPs involved. We've got our source and destination ports. And then down here at the bottom, you can see the certificate or public key that's been transferred. So in this case, I was going to a website, subdomain of badssl.com. Last line here, you can see this is the certificate authority. So we are presenting to my client, hey, this is a certificate for badssl.com. And then here's the certificate authority that went ahead and signed that certificate. So with this data, what can we do with it on the firewall side? Well, when it comes to intrusion prevention, we're looking for traffic patterns, we're looking at the packet body and the packet headers. With encrypted traffic, our packet body is encrypted. Firewall can't see that. It's not going to be able to inspect that with intrusion prevention. Same with traffic patterns and anomalies, where visibility is limited there. However, any IPS rules that are based on source destination IPs or source destination ports, those are still going to work. Gateway antivirus, we lose all visibility here. We're not going to be able to do a hash of the file. We're not going to inspect any of the archives. We're not going to be able to send that file for any sort of sandboxing in the cloud. Application visibility, for the most part, still works. We can use the common name off the certificate on the exchange, then we can get the URL or FQDN out of it. We can see the packet headers as well. We're just not going to be able to see anything in the actual payload itself. With web filtering, same thing. We've been able to filter web traffic up until this point via that certificate exchange. That certificate is going to have the common name and the URL, and that's how we're going to be able to match those categories and URL lists. Keyword filtering for search terms, any sort of content filtering, that's not going to work just because we're not going to see the content of those HTTP gets and posts as that traffic goes along. And on our threat feeds, we're still going to see IP addresses, we're going to see FQDNs. Mileage may vary, though, on the hoodie-wearing hackers of how well those are matched with those feeds. All right, so TLS 1.3. So with TLS 1.3, as we discussed, that certificate, when it is sent between the server to the client, that's not visible to the firewall anymore. So at this point in the firewall side, with encrypted traffic, all we can see is we can see source to destination IP, and we can see source and destination port. So when it comes down to IPS, we've now lost that certificate common name, or sorry, application visibility. We've now lost that certificate common name. We still have the packet headers, we can still see source and destination ports, but that's about it. Web filtering goes completely out the window. We can't see that certificate common name, we can't see the URL. We basically lose visibility or the ability to filter web traffic with TLS 1.3. And then with the threat feeds, same thing, we lose those FQDNs to be able to use in threat feeds. So kind of looking through, recapping, TLS 1.2, encrypted traffic does cause some issues with firewall visibility. Some services work, some don't. And then with TLS 1.3, and with it becoming the majority of traffic, we lose access to most of those firewall features that we have known for a next generation firewall. We're kind of back down to, we've got a stateful firewall. We are allowing traffic in and out, but we're not expecting it like kind of we thought with buying the shiny firewall with all these features and subscriptions. So what's the solution? Well, SSL inspection. So this is the ability to look at that SSL traffic, potentially decrypt it, and then get our visibility back. Two types of SSL inspection I want to talk about. First one is known key decryption. So in this scenario, your firewall is aware of the public and private key, that actually those are uploaded to the firewall of your, in this case, servers. It can see that TLS handshake, and it can actually decrypt that TLS handshake with that private key. This allows us to grab these session keys from that and actually have visibility into that encrypted traffic. This really only works, though, for servers because you need to have the private key of that server to be able to upload it to your firewall. My client is not going to have a public certificate, things like that. So this is really just best for protecting servers in your environment. The other thing, this is not going to support TLS 1.3. Because that certificate handshake is not visible to the firewall, there's no way for the firewall to know, okay, here's the public key being used, here's how I match it with that private key to go ahead and inspect that traffic. So kind of looking through a kind of rough idea of the known key decryption. So similar thing, I've got plain text data. I'm going to encrypt it with a public key, get my cipher data, and then I can split the traffic off. It can go ahead and go to the server, it can decrypt it with its private key, and get the data. On the firewall side, it can decrypt it as well, get that data, and then we can run it through all of our firewall inspection engines. From there, it can send a TCP reset, things like that if needed, to go ahead and drop that traffic. The other side of decryption is what I call TLS intercept. So this is the firewall actually gets in the middle of that initial TLS handshake and interjects itself. It's going to create technically two TLS legs, one between the client and the firewall, and then another between the firewall and the server. This gets us in line. Big thing with this is, since that firewall is now in line with the client, it is going to be re-encrypting traffic. So rather than the certificate from the server being presented to the client, now you have the certificate from the firewall being presented to the client. What do we know about certificate authorities? You have to verify ownership of a domain to get a certificate. I can't go and get a firewall or a root certificate for my firewall that's out there and widely trusted, because I don't own every domain out there. So clients have to trust that firewall public key. We have to push it out via MDM, GPO, those sorts of things. Or everyone gets those certificate warnings, and hopefully they don't click accept. The other great thing here is it supports TLS 1.3 for the most part. There's some vendors out there that don't support TLS 1.3 decryption yet. What they actually do is they spoof a response from that web server saying, I don't support TLS 1.3. Go ahead and go down to TLS 1.2. So sometimes they support TLS 1.3, but it's actually downgrading to TLS 1.2. It really isn't a solution going forward. And really for these vendors that don't support it yet, we're just a vulnerability away in TLS 1.2 for all of our auditors saying, okay, no more TLS 1.2, TLS 1.3 only. It really isn't a solution there kind of going forward. All right, so looking at the handshake here, same idea. We've got our data. We're going to encrypt it with our public key, get our cipher data. The firewall is going to use its private key to go ahead and decrypt that. We can then do any sort of security functions we need. We're then going to go ahead and re-encrypt that traffic with the server's public key and go ahead and send it on to the server. Show you real quick Wireshark, just one thing, because I love Wireshark. What you kind of see here. So this is that same TLS 1.2 handshake that we looked at earlier. The big difference here is now you can see down here at the bottom, the root certificate that's being presented to my client is actually from my firewall. Here it's a FortiGate 60F firewall. So it's actually re-signing that traffic, still presents the certificate from the website I was going to, but now the root or the authority that signed that is my firewall. So great, we solved all of the world's issues. We can just decrypt all of the TLS traffic. No problems. Well, there are some problems with TLS decryption. It's one thing we can't do it across the board, and we need to be aware of some of the caveats. So first up, TLS decryption is firewall resource intensive, very, very high on the CPU cycles. A lot of vendors have a 50% reduction in throughput. Some have a much higher reduction in throughput. Really kind of depends on the vendor and how well they can offload that to hardware. That's where you can get some of the pretty good throughput there. So the big thing here is let's be selective. I don't need my Veeam offsite backup job to be decrypted by the firewall. I maybe have a SaaS app to a vendor that I trust. I don't need that to be decrypted when that goes to the firewall. So that's some ways to reduce that throughput burden on the firewall. Client support, like we talked about, those clients have to trust that certificate on your firewall to be able to push traffic. I can't push that certificate to a non-managed endpoint. Say I want to decrypt all the traffic from my IoT devices. Those aren't managed. I can't push a certificate to those devices. I can't decrypt that traffic. So it's being selective. Hopefully you've got subnets. Maybe you can do it on basically an IoT subnet. Say, okay, I'm not going to decrypt that traffic to that subnet. Certificate pinning. This is big in the mobile world. Basically, with certificate pinning, the application doesn't actually use the trust store from the operating system. It's going to say, okay, I'm going to hard code my application to only support a specific certificate. There's no way to update that application in a way to say, no, go ahead and trust my firewall certificate anyway. So this is also being selective. On some of my testing and things, even my apps on my MacBook, Apple apps, appear to have some sort of certificate pinning. You turn on TLS decryption, those apps stop working. So it's being selective and rolling this out kind of in a ordered manner to know, okay, what breaks, what can be decrypted, and what can't be decrypted. And then privacy issues. So I was going to go through this. My initial thought was, okay, yeah, we've got PHI, HIPAA, GDPR. We can't decrypt anything. You can actually make the case that with these standards, we need to decrypt things. We need to know what traffic is leaving our network. We need to know what's in that traffic. we need to be able to protect if protected health information is in a file upload. So in a lot of ways, decrypting traffic actually supports these standards, but at the same time, users have to be aware of this. You can't just go and say, I'm going to go ahead and decrypt maybe a guest network or public Wi-Fi, those sorts of things. So it is based around internal policies. Do you have your acceptable use policies correct? Are people aware within your organization that any traffic can be inspected and will be inspected? So that's on the firewall side. We're going to decrypt traffic. That's how we're going to solve this. But maybe, is there another way to solve this? Are there other tools we can use? One way we can solve this is secure internet gateways. So that is through companies like Zscaler, Cisco Umbrella. Rather than try to deal with this locally, let's send it up to the cloud. They've got the cloud scale, the resources to manage it. They can do this for us. And everything they do is specifically built for decryption. It may add some latency potentially because you're now having to ship that traffic up to the cloud and go out. But that is one way of handling it outside of the firewall. Another would be defense in depth. Hey, if the traffic's decrypted or encrypted, my gateway antivirus isn't going to work. Well, maybe I don't care. We've got our defense in depth. We've got our MDR, XDR, whatever the three-letter acronym that marketing has come up with now for that's on your endpoint. That's going to handle that. So maybe there are some solutions where, okay, we lose that visibility. It may not be as big of a deal. Same thing for web filtering. With Cisco Umbrella, they have DNS-based filtering. Maybe we handle it there rather than relying on the firewall for that web filtering. And then one area, last area that I'm pretty excited about is encrypted traffic analytics. So Cisco has been a big proponent of that, a lot of research here. Rather than saying, okay, we've got to decrypt all of our traffic to know, can we take traffic samples that are known to be malicious? Can we run those through ML AI? Can we start to build baselines to look, okay, let's use this machine learning to say, okay, this SQL injection attack is 10 packets, and we know that 5 of those packets are 500 bytes, 5 of those packets are 200 bytes. Can we go ahead and build models to then go ahead and detect that traffic without having to decrypt it? So that's another thing I'm excited about in the industry is what can we do kind of outside of the box rather than just hitting with a hammer and interjecting that traffic and decrypting it, maybe potentially having some privacy issues, performance issues, those kinds of things. Let's actually look at that traffic without having to decrypt it. All right. And that's what I have for you. Happy to answer any questions you might have. Otherwise, have a great day. Yeah, thanks.